Testing, testing, 1, 2, 3, 4. 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 Hi everyone, welcome to today's machine learning class, and hopefully you are done with your homework 1 and are looking forward to homework 2 coming today. Yay! Okay, I saw some active discussions on Slido about homework 1 and homework 2. Anyway, homework is a very important part of this course that encourages you to strengthen the knowledge that you have learned in class and also extend the knowledge outside of the class. So as you have seen in homework 1, we not only have problems that are closely related to the materials inside the class, but we design some extensions to help you explore some other knowledge outside of the class. Okay, so this is our design, okay, not a bug. And similarly, we will have homework 2, homework 3, and so on, following this principle. And most likely homework 2 will be harder than homework 1. Okay, but anyway, that's part of the learning process. I hope that you have learned something new throughout the homework. And if you find that you cannot catch up with the homework progress, you'd better try to move to a faster pace as soon as possible, because we have homeworks that keeps coming in and they'll be harder and harder. So if you do not understand what we have taught now, it will be harder and harder for you to follow up. Okay, so if you have trouble with learning the knowledge that we have taught so far, please do consider visiting the TA hours to really understand what we have taught. Okay, so let's get started with today's class. Actually, we're not done with last week's class yet with the theory of generalization. We have talked about an important theoretical tool called the VC dimension, basically. Okay, and today we will discuss more about the message behind the tool. So let's first review a bit about what VC dimension is. Okay, so we started discussing the breakpoint and so on to show that our hypothesis set can be limited, okay, with some inputs, okay, and the limitation is called a breakpoint, and we consider naming the most powerful aspects of the hypothesis set as the VC dimension. So the formal definition is the maximum non-breakpoint. Okay, and by non-breakpoint, I mean there must be some combination of the input vectors that allow shattering. And if you recall, shattering means producing all the possible dichotomies on that set of inputs. Okay, so if we get the VC dimension to be something, okay, then the next number is the breakpoint. For example, if VC dimension is 3, then 4 is the breakpoint. Okay, so 3 having some 3 input vectors that can be shattered, 4 none of the input vectors can be shattered. And this is going to be important for the first part of the class. So if you are still a little bit confused, please try to write down some notes, okay, beside you, okay, so that you can follow what we're talking about. Okay, so starting from the VC dimensions, let's do some review. We have encountered some hypothesis set. For example, we discussed positive rays, where if you only have one input vector, positive ray can produce both dichotomies very easily. While if you only have if you have 2 input vectors, then there's one dichotomy that cannot be produced, and therefore breakpoint 2, VC dimension 1. How about positive intervals? Well, if you have 2 input vectors, the positive intervals can produce all possible dichotomies as long as the 2 vectors are different from each other. VC dimension 2. If you move to 3, and then there's one dichotomy that cannot be produced, in particular the one with negative in the middle. And in that case, that's a breakpoint. So VC dimension 2, breakpoint 3. Okay. That's going to be important for our discussion today. And actually, last time we played with 2-dimensional perceptrons. And we showed that if you have 3 input vectors placed as a triangle in some way, then we can produce all the possible 8 dichotomies. But if you have 4 input points, then what will happen is that we can at most produce 14 different dichotomies, not 16, 14. So 4 input vectors, breakpoint. 3 input vectors, VC dimension. Okay, so that's what we're going to talk about today. And following this, and we hand-wavingly told you about the VC bound and also its extension to the noisy case. Let's revisit what we have known so far about the perceptron learning algorithm. Starting from a linear separable data set, we can use the perceptron learning algorithm and ensure that it can converge. Okay, that's what we have proved in the very first class. Then, after we let the algorithm run for enough iterations, we can guarantee that E in equals 0. So that's the training guarantee of the perceptron learning algorithm, as long as we let the algorithm run for large enough under the assumption that the dataset is linearly separable. And we generally don't know how large T needs to be, okay? But let's assume that it's large enough, so we actually get a perfect line in 2D to separate our training examples. That's part of the story. And the other part, now if we assume that the dataset that we have on hand is generated from some distribution, okay? This some distribution was initially saying the input is IID from some P and Y is from a target function. That target function can be linear or nonlinear, okay? It doesn't matter to us. It's only matters as long as the eventual dataset is linearly separable. Okay? And last time we also extended this setting to say, okay, this generation can also be noisy, okay? Meaning XY just follows a joint distribution that doesn't need to have a clean boundary represented by F. But anyway, okay, let's assume that our dataset has this following underlying process for generation. Then, by the discussion we have last time, first, we know the VC dimension is 3. And second, we know that we can get some guarantee. Okay, and with this guarantee, if we have enough examples, we can make sure that the bad probability is very small. That is, with a high probability, everything is good. E in is close to E out. And we make a belief on that, E in is close to E out, and then combining the red path and the blue path, we finally will be able to claim that E out is close to 0. And the key part, okay, in addition to the VC bound that we taught last time, was that we are able to claim that the VC dimension is 3. The VC dimension of the 2D perceptron hypothesis set is 3. And how did we do that? We did that by playing with input combinations, saying how many dichotomies can we generate and so on, to the extent that we confirm the VC dimension to be finite, the VC dimension to be 3. Okay, so now we mentioned that the beauty of the PLA algorithm is that it can be applied to more than 2 features. Okay? So if you have 2 features, 10 features, 100 features, 1126 features, it doesn't matter. You run the same algorithm, everything is kind of vector operated and so on. The theoretical proof is vector operated, and therefore it seems that on the red path, okay, it doesn't matter whether we're using 2-dimensional or 3-dimensional or more dimensions. But for the blue path, we're not sure yet. Okay, if I give you a data set of 10 dimensions, okay, and ask you to run the PLA algorithm, then we don't know what would happen because we do not know whether the VC dimension for that part is finite or not, or whether we can confirm the VC dimension to be of some specific value. And therefore, this is what we're going to do. We're going to prove the theoretical guarantee behind general PLA by proving the VC dimension of the perceptron hypothesis set for arbitrary dimensions. Okay, now let's do some observations first. Okay, actually, we have almost told you about 1D perceptron. We told you about positive rays, okay? And if you think about it, positive rays is just half of the 1D perceptron, and the other half will be negative rays, okay? So the symmetric part and so on. If you follow the same discussion that we had last time and manually analyze the VC dimension, you would get that the VC dimension is 2 for 1D perceptron. 2D perceptron, VC dimension is 3, and we talked about what can and cannot be shattered by 2D perceptrons. Now, we can make a conjecture here, okay, that the little d dimensional perceptrons will be of VC dimension d plus 1, little d plus 1. Of course, that's just a conjecture. Okay, one thing you should learn from this machine learning class is that you cannot predict a general formula by looking at only 2 numbers, or at least not without any other assumptions. Okay, so we need a formal proof, okay, not just conjecture. Otherwise, I'll be just saying, okay, you are making a time series prediction with 2, 3, and then the next number. That doesn't seem to make sense. So what we're going to do here is to give a formal proof that the VC dimension is indeed little d plus 1 for perceptrons in little d dimensions. There are 2 steps here. One is to prove that the VC dimension is larger than or equal to d plus 1. And the other step is to prove that the VC dimension is less than or equal to d plus 1. Then if you combine these 2, you would get exact equality. To guide you through this proof, let's first think about what condition we need to get us to the very first step. We want to prove that the VC dimension is bigger than or equal to some value. How do we prove that? So that's the question that I'm going to show you here. And please answer them on Slido. I just announced it. Okay, we'll give you like 3 minutes, okay, to answer them on Slido. Okay, thank you for participating on the task. And we've seen some results here. And also, I've marked the correct answer there for your reference. Okay, let's. I think this polling has a benefit that we know your most confused part. Okay, so let me answer it a little bit. Okay, the most confusing item seems to be between 1 and 2. There are some inputs that we can shatter, or we can shatter any set of inputs. Now, if you are confused, think about what we did for 3 input vectors in 2D perceptrons. 3 input vectors, 2D perceptrons, we have 2 cases. One case, we have this set, okay, 3 points, and put it in a triangle, and we say we can shatter those, okay, because we can produce all the 8 possible dichotomies with the perceptrons. On the other hand, if we also have 3 input vectors, but put them on the same line, then we cannot shatter. Okay? So in this sense, we cannot shatter any set of D plus 1 inputs. We cannot shatter any set of 3 inputs here, but we are still able to say, we're advancing the VC dimension because we have seen one set of witness, okay, one set of input vectors that tells us, yeah, shattering is possible. Please move on to the next number. So to show that the VC dimension is greater than or equal to something, we just need one example to make sure this can be achieved before moving on to the next one. Or in terms of the growth function, remember the growth function says the maximum number of dichotomies that can be produced on any set of input points. The maximum number of dichotomy n h of n, the maximum that can be produced on any big N points. So any 3 points, any arrangement, maximum number of dichotomy. And VC dimension says the maximum number of dichotomy must be equal to 2 to the n. Okay, so on the part where the VC dimension is satisfied, it's not a breakpoint zone yet. We need to find shattering. We need to find 2 to the n. Okay, that's why we want you to choose item number 1 here. By definition, there are some inputs that we can shatter. In the 2D perceptron case, that's the red case here. And if we can identify that some inputs, then we can move on to checking D plus 2, D plus 3, D plus 4 to see if we can reach the VC dimension. Okay, so we're starting from the smaller number, see if we can shatter, and move on to the next number. That's why the answer is 1. And we're not moving to D plus 2 yet. Okay, D plus 2 is next number, but to show that VC dimension is greater than or equal to something, we're moving from the smaller number to the bigger number. So we just need to show that D plus 1 can be achieved. Okay, regardless of whether D plus 2, D plus 3, D plus 4 can be achieved or not. That's what we're going to do in terms of proving here. Okay, so let me turn off the Slido here. The Slido presentation here. Okay, and I'm going to also take the opportunity to move to see if there are some questions that I can answer here. Okay, there are something about homework 1, homework 2, quitting or dropping. I'm going to not answer them for now. Homework 1. Oh, okay, great. So everyone is just concerned with the homework, not with the lectures we're teaching here. So let's move back to our proof. Now, if you follow the proof, the only thing we need to do to prove that VC dimension is lower bounded as D plus 1 is to find some inputs that we can shatter. Okay, so what's the sum inputs that we can find? Let's look at this. Okay, let's construct a matrix, okay, that organizes the input vectors that we have on hand. I'm going to have x1, x2, blah, 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 until xd plus 1. And I'm going to arrange the matrix this way, okay, saying that the diagonal part is always 1. And also the first column, okay, which corresponds to x0, actually is always 1. Other parts are 0. What inspires me to do that? In two-dimensional, it actually means these 3 points that form a triangle. Okay, there's 0, 0, and this is 1, 0, and this is 0, 1. And also remember, we padded a 1 in the very beginning as our x0. Okay, so if you check those 3 vectors, this is the x1 shown above, this is the x2, and this is the x3. Okay, so consider an X matrix that organizes those vectors. One thing that you can notice and you should convince by yourself is that this particular matrix is invertible. Why is invertibility important in this problem? Well, let's consider this particular inputs and see what we can do with perceptrons. When we are saying shatter, the process that we have in mind is that I give you any dichotomy that I want to produce. You should tell me a corresponding W. Remember, that's the process we followed last time. I say, now I want to implement this. Can you find a perceptron? You say, yes, I can find a perceptron like this, and this is the particular W. So if I can provide you with any dichotomy here represented by a vector y, and you tell me the corresponding W. Okay, you tell me the W that implements or achieves this dichotomy, then we can do shattering. So let's see algorithmically how we can possibly do that for this special set of input vectors. What we want is to produce this dichotomy, which can be represented by this condition. If I multiply the weight vector by our input matrix here, okay, after the weighting, you see that you basically get something like sine of x1 transpose w, sine of x2 transpose w, sine of xd transpose w. So multiplying this matrix by w and taking the sine basically gives us the output from that line, from that hyperplane, from that perceptron. And we want, after taking the sine, the result to be equal to the y vector. That means we produce the dichotomy. If we can do that, that's cool. And one sufficient condition for doing so is to require that xw equals y exactly. Okay, if after multiplication, of course, all those floating point numbers and so on, you magically get a particular y, okay, a particular value that's equal to every y that you want to get. That's cool, because if you have got those particular y, then after taking the sine, it's still those particular y. So that's a sufficient condition. Not necessary, but sufficient. Of course, it's a hard condition to meet because you are arguably summing lots of floating values and so on, but you want exactly positive 1 or negative 1 as the output. Now, mathematically, can we achieve this? Yes, because X is invertible. So you can use one particular solution from linear algebra to achieve this. Basically, taking the inversion of X and multiply by Y. You get the W that can achieve this. So what do we do here? You challenge me with any Y you have in mind. I tell you this W can implement this particular dichotomy because And this W multiplied by X get me the exact Y, which gets me the exact Y also after taking the sign. So any Y can be implemented. And this tells us that any dichotomy can be implemented, which means shatter. Yay! So by taking this invertible matrix, actually you can imagine you can take any invertible matrix. I just take a simpler one to justify the claim, or a simpler one that you may be able to imagine that it's invertible more easily. But as long as you take an invertible X, you can produce any dichotomy by the argument below. And therefore, by having this special X to be shattered, we prove that the VC dimension is greater than or equal to D plus 1. Half done. Yay! Now, let's see how we can prove the other way around. Okay. The other way around needs to show the VC dimension is less than or equal to D plus 1. Not greater than or equal to, but less than or equal to. And we have the same 4 choices for this problem. And let me turn on the Slido. Similarly, let me give you 3 minutes, okay, to input your answer on Slido, and then we can discuss afterwards. Please enter your choice on Slido. Okay, great. Thank you for providing your inputs here. And most of you have chosen that we cannot shatter any set of D plus 2 points, which is the correct answer, given that this actually tells us that D plus 2 is a breakpoint. Okay, when d plus 2 is a breakpoint, it cannot be a VC dimension, and therefore VC dimension must be strictly smaller than that, okay, which gives us the inequality that we want. And there are some confusions about whether this should be mixed with d plus 1 inputs that we can shatter. Well, if we're just talking about upper bound, no. Okay, when we say we can shatter something, it pushes the lower bound. Okay, it tells us that we need to move to a bigger number for VC dimension. While if we are talking about an upper bound, VC dimension is smaller than or equal to something, then we may need to move to the case where we're discussing what we cannot shatter. Okay. Now, some of the confusion are from choice 3 and 4. We cannot shatter any sets, or we cannot shatter some sets, okay, or some of the inputs. Well, if we're just talking about some cases, okay, for example, 3 input vectors not in general position but on a line, or even worse, input vectors that are duplicates with each other. You can see that we cannot shatter those points. Okay, if points are duplicates with each other, you cannot assign positive on one point and negative on the other points because they are just the same points. So basically, having some inputs that we cannot shatter always happen. Okay, there are always some inputs that we cannot shatter. But remember, when we talk about the growth function, we talk about the worst case where we can arrange the inputs arbitrarily. Okay, so, and we care about the maximum number of dichotomies. And therefore, even if there are some input cases we cannot shatter, they may not matter because they are not the ones that achieve the growth function. We need to find the inputs that achieve the value of the growth function, the maximum values there, in order to identify whether that case belongs to the breakpoint or the VC dimension. VC dimension, we can shatter some inputs. Breakpoints, we cannot shatter any set of inputs, with that number, of course. Okay, great. So having clarified that, let's move to the proof. And this particular proof will be slightly harder than the previous case, as you can imagine, because we talk about we cannot shatter any set. Cannot shatter any set actually means what? I provide you with a set, you say no, 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 no. I provide you with another set, you need to say no, 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 no. And actually, there are infinite number of sets, and you always need to say no, 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 no. Now, if we're just discussing individual cases and you keep saying no, that would be a little bit ridiculous. So we need to find a general contradiction. Okay, what would happen if I provide you d plus 2 inputs that's doomed to fail? That's contradictory. Okay, that's the concept we're going to use here. I provide you a set, you find a contradiction within, and then basically it is a function, okay, that I can keep calling to query whether it's possible, and you can find a general contradiction that would complete our proof. Okay, so let's see. Now, before we move to the general case, let's look at the special case. Okay, remember in the special case before, okay, we use points arranged in specific positions and so on. Now let's look at a special case to get some insights about how we are going to make the general proof. This special case is as follows. Okay, I'm putting them as a square into D, and basically, as you can see, it is just extending our previous case by one vector. And for this one particular vector, it is this one. Okay. Now, why is this special? Because it creates some restrictions. Let's see one particular dichotomy that cannot be implemented with this special case. If I have circle on those two vectors and cross in this one, and I'm saying I want to implement a dichotomy, this actually tells me that this vector, this new vector that I added, must be circle. It cannot be cross. Why is that? Well, you now use your visual inspection with your human intelligence. I believe it's not that hard to draw the conclusion that it must be a circle if I want to make the first three correct. Okay, that is, to make the first three correct, it creates some restriction such that if I insist that this guy to be a cross, there will be contradiction. That is the basic idea we're going to use here. We're going to assign a dichotomy that is totally impossible to construct. And this particular dichotomy would have the first three or the first few inputs, first few labels fixed, and then we decide the final one such that the final one is impossible. So that's what we're going to do here. Okay, and formally, mathematically, what happens within this proof is that if I want to implement the first three correctly, what do I need to do? I need to have the first three be in this two circle and this one cross. To have this one cross, remember this one is the origin, so I need to have this W negative. And the negative one multiplied by this x0 here would give me the cross that I need to have. Okay, so this is, let me quickly put the sign that I want my W to have to achieve this. And I need, with this one being negative, I need this one being positive and this one being positive in order to produce something positive for these two vectors, to make these two circle. Okay, so to implement those three, I basically have plus, plus, minus decided by the dichotomy or the labels that I need to have. Then let us quickly see why it results in this guy being forced to be positive or cannot be negative. Why is that? Well, I have this negative guy, this positive guy, resulting in plus already, resulting in positive already. Now I add something even more positive. So when adding this even more positive, I get something positive. That's the mathematical conclusion we can draw by having those. And this is actually the consequence of linear dependence, because if you check the above, by construction, I made my x4 to be x2 plus x3 minus x1. You can easily check from the above. What does this mean? It means that if I have some W such that W multiplied by x1 is negative, W multiplied by x2 is positive, W multiplied by x3 is positive. That's basically the dichotomy you see here. If we have this, then we are doomed to have this guy be positive, because it's a positive term plus a positive term minus a negative term. Overall, everything is positive. So linear dependence, the linear dependence that I constructed in this case, forces the outputs on the fourth point to be positive, not negative. That's the concept we're going to use in the next proof. linear dependence forces dichotomy of dependent vector. Okay, linear dependence, this X4, depending on those three vectors, forces some of the dichotomy, okay, of the new vector or the final vector that we added to the set. Okay, so let's see what formally we can do for the general case. Okay, we cannot just prove for the special case. Remember, we need to prove for the general case. And for the general case, we need to first write down the linear dependence. And the linear dependence can be arbitrary, right? Okay, but linear algebra tells us because our vectors are in a d+1 dimensional space. Now you have d+2 vectors. You must have linear dependence, meaning this xd+2 can be a linear combination of all other vectors, all the previous vectors. And this linear combination has some coefficients. Okay, those coefficients are very important for us in the next step of the proof. We, in general, the coefficients can be anything, but we know there's a particular set of coefficient that achieves this linear dependence. Now, with this linear dependence, I am challenging whether we can generate the first one the first label in the dichotomy being sign A1, the second label being sign A2, the third label being sign A3, and so on until the d+1 label being sign AD+1, and then the last guy being cross. So this is what we did previously. I'm fixing the first ones to some particular labels, and then challenge with the last one that's logically impossible. Okay, so when the first ones are these particular labels, then what happens is that when you take the linear, the inner products that we use in perceptrons, the first part of the vector produces a circle as you wish. The second part produces a cross as you wish because you designed those to follow the sign and so on. So for this particular W, if we say we can have some W that achieve this, then this must be satisfied. All those values in terms of their sign must be achievable. Then what happens is that we have a term that's positive. Oh, sorry, I should draw a particular term that's positive. Why is it positive? Because it's A1 multiplied by sine of A1. Okay, of course, timing some value. Okay, but anyway, in terms of the sign, it's positive. We say that that particular W can achieve this, so it must output something that corresponds to the sign of A1, and that's positive. Similarly, this whole term is positive because it's A2 multiplied by the sign of A2. Now, this guy must also be positive because it's AD+1 multiplied by something that corresponds to the sign of AD+1. So all positive terms summing together, this guy, this result must be positive. But now I'm challenging you to implement something negative on this. Is it possible? No. After fixing the first the signs of the first predictions, the final prediction must be positive. It cannot be negative. That is, if I insist on generating a dichotomy with the last guy being negative and the first parts following the sign from those linear combinations, it's not possible. It's a contradiction. And when there's a contradiction, we say, so for any d+2 inputs in your X, because of linear dependence, you always find a dichotomy that cannot be implemented. And this particular dichotomy that cannot be implemented tells us that there's no shatter, and therefore d plus 2 is a breakpoint, and VC dimension can only be smaller. That's why the VC dimension is less than or equal to d plus 1. Okay, so that's the proof we intend to take here, and understand that it's a hard proof, so you may have some questions and so on. Let's because we used some time in the question answering before, let us take a 6-minute break this time, and you can also input your questions here and so on before we continue. Okay. Now, thanks for coming back. We see lots of questions on Slido. Let's try to answer them as much as possible. Can we explain shatter with Mandarin? It seems different from what it means. Okay, if you go query the meaning of shatter, in Mandarin, it's actually means 打碎, okay, or splitting into pieces and so on, okay? And in this context, shatter actually means be able to produce all dichotomies. OK， 可以产生所有的 pattern。OK， 可以产生所有的 dichotomy， 就叫做 shatter。所以，如果我给了你一些 input vector， 然后呢，你发现你的 hypothesis set 在这些 input vector 上，所有的圈圈叉叉的排列组合都可以产生出来，这就是 shatter。So if you see that all possible dichotomy combinations can be produced on a particular set of input vectors, we say we can shatter the input vector. Okay, and there's one request about explaining why xw exactly equals y. Now, I'm assuming you refer to the previous case where we compute this particular w. Okay, we know x is defined above. We know the y that we want to increment. We compute this w, this is fully computable, and get w. What's the property that this w must satisfy? This w must satisfy xw equal to y, because that's just x minus y, which this cancels out to be an identity matrix which must equal y. Okay, so in terms of proof, what happens here is that for every dichotomy that we want to implement, we compute this w. This w must satisfy that xw exactly equals y, which in turn must satisfy the sign of xw equals y. That's how we say we can implement the dichotomy. Can we explain the mathematical notation again? What does this X matrix mean, and why can it be written as a 0-1 matrix? Okay. Now, what does X matrix mean? X matrix just gathers the input vector that we want to consider in its rows. Okay, so every row contains an input vector. Remember, in the general case, we have a set of input vectors, and we want to see whether we can shatter those input vectors or not. And because we want to use linear algebra more easily, we arrange those those input vectors in a matrix. Okay, and this matrix tells us some properties that we use in the proof. And because, okay, to prove that VC dimension is lower bounded, we only need one particular set. Okay, remember this was the part in our first practice, and I constructed this particular set to be this value. Okay, you can construct other sets too, but I constructed it to facilitate my proof. And this construction has its physical meaning that it looks like something, a very particular triangle in 2D. And visually, it can tell us that it seems to be easily invertible. Of course, you can try to prove that. Why can we assume the first column to be y? And this corresponds to our x0. Remember, we padded all our input vectors to have x0 equals y, and that column represents x0. Well, homework 2 also contains 16 questions. Is it possible to give a little less number of questions, fewer questions? And homework 2 would have 16 questions. Okay, and in general, every homework this year have 16 questions, and we're not considering to lower it further, because actually we decreased it from the previous year. Last year we have 20 per homework, and this year we have 16. Okay, so we are already experimenting with fewer questions this year, and it is very unlikely that we're going to further decrease it. Okay, now 38, page 38 seems to be a special case too. That's a very good comment. Actually, page 37 is a special case, while page 38, we are intending to use this proof to all general cases. Okay, so the special case in the previous page was meant for building our physical understanding of the problem, while for this general case, I'm writing down x1, x2, up to xd plus 2, not by any special value, okay, any general value, but linear algebra tells us as long as I have more than d plus 1 vectors, there must be linear dependence, okay, that I can express with this linear dependence equation. So on page 38, we're working on a general case, not a special case. So we're proving that adding a final input can cause the dichotomy to fail. Yes, indeed, we're showing one dichotomy that basically cannot be implemented with the final inputs by the linear dependence. Can we increase the English prioritized TA hours? Let me double check with the TAs about that. And most important thing is we need to understand the usage, okay, the usage level of different TA hours and so on, and also the TA's capacity in order to decide that. For now, I don't have the data yet. Okay, so let me learn from the TA's data to decide that later. Okay, there are some particular questions. Let me answer. So there's the first column padded with 1. That's the default. That's the x0 that we have answered. And okay, now why is there linear dependence on x1 to xd plus 1? And I'm afraid that you need to ask this question to your linear algebra teacher. Okay, so that's the part that your linear algebra or background knowledge should tell you, and we cannot explain it in super detail in this class. Okay, similarly, okay, there's linear dependence and so on. Please check your linear algebra textbook. Okay. And d plus 1, d plus 2 examples in a d-dimensional space, there must be linearly dependent. Indeed, actually, the reason we need d plus 2 is that our vectors are effectively d plus 1 dimensional by padding the 0 components. Okay, so linear combination and so on. Yes. Okay, so basically, thanks for the many of your comments to help your classmates understand the context. Okay. Now, let's answer more questions about this page where people still have concerns on whether it's a general case or not. Okay. Let me say this. Page 37 that I show here, special case. Okay, that's definitely a special case because I listed the vectors that I use and so on. Page 38, general case. I didn't specify the particular x1, the particular x2, and so on. Mathematically, all I know is that there's a linear combination, and I can mark the coefficients of the linear combination by their signs. And that's actually what I did here. So that's the distinction between special case and general case. Here we are having a general case. And when we're having a general case, now what happens here is we need to start from this general case to see what cannot be implemented. So let me state the proof again. From the general case, we get the linear combination coefficients. We use these coefficients to construct a dichotomy. In this particular case, the dichotomy is circle, cross, blah, blah, blah. The last one is cross. And the very last one, that's d plus 2, I'm going to name it to be the cross. I'm going to claim that this is not possible. Okay, by contradiction. How do I prove by contradiction? Let's say this is possible. When this is possible, there is a W that can be used to implement this. What does this W need to satisfy? It needs to satisfy W transpose x1 to be positive, W transpose x2 to be negative, blah blah blah, W transpose xd plus 1 to be negative. Okay, if you say this is possible, okay, if possible, then there's a W and W must satisfy this. Then what would happen if I put this sign back to the linear dependence equation? I can construct A1 W transpose x1 plus A2 W transpose x2 blah 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 plus AD plus 1, and then I get a positive term, because it will be a negative guy multiplied by a negative guy, that's W transpose x2, multiplied by a negative value, A2, that gives me a positive term, and so on. So I get lots of positive terms here. I sum them together. What do I get? In terms of the equation above, I get W transpose xd plus 2. And that's a bunch of positive guys summed together. That's forced to be positive. And it cannot be negative. So that's the contradiction. Okay, so that's the proof that we use to show that this particular dichotomy that comes from the linear dependence coefficient, the linear combination coefficient, and a particularly designed negative label is not possible. So this is a general proof. Okay, from the proof, I'm not using any particular vectors and so on. I'm just using the facts that I can get from linear algebra. Okay, so we're showing that one dichotomy cannot be implemented. That's totally enough, okay, to say it cannot shatter. And we're not saying what happens to other dichotomies. Maybe they can be implemented, maybe not. So we're not assigning their positive or negative. We're just showing the most impossible case and justifying that this most impossible case cannot be implemented. Okay, so yes, so the W is perfect from x1 to xd plus 1, and then we find that the last one cannot be done. Okay, we explain why it means for this to be general. We explain why we only need one dichotomy, okay, to show the case, one particular dichotomy, such that the predictions exactly follow the sign of the combination coefficients. And we explain why this has to be positive, because it's a negative value multiplied by a negative value. And why is this AI the same sign as W transpose I? That's our assumption by the possibility. If you say it's possible, you must be able to find a W such that this W achieves this. Okay, so we assume the existence of this W and then prove by contradiction. And why is that negative? Okay, we answered that. Okay, so we resolved all the questions here. Now we are finally able to claim that the VC dimension of perceptrons is little d plus 1. I spent a little bit more time on this because this is hard but important for you to understand or appreciate the values of the VC dimension. Okay, so let's see a little bit some of the meanings behind the VC dimension. Okay, VC dimension sort of quantifies the degrees of freedom in your hypothesis set. In this particular perceptron case, we have the hypothesis parameters to be the W vector, which is d plus 1 dimensional. So this is kind of like the degree of freedom with your hypothesis set. And when we say the hypothesis quantity, it's another way of looking at the degrees of freedom, but only by its original number of hypotheses. While basically we are talking about this hypothesis power to be a binary degree of freedom. And when we do the VC analysis, okay, sometimes we just say physically, it means we're trying to calculate the powerfulness of the hypothesis set by evaluating its binary degrees of freedom in terms of how or whether it can shatter some binary input vectors, and we get D plus 1. So this is the physical meaning behind the VC dimension, and actually this concept of degree of freedom can be used, okay, when you look at your future machine learning models to try to estimate its powerfulness. Let's look at some of our old friends here. We have the positive rays, and remember we say for the positive rays the VC dimension is 1. And it so happens that this learning model has one free parameter. Positive intervals, 2 free parameters, and you get the VC dimension to equal to 2. And perceptrons, D plus 1 free parameters, you get the VC dimension to equal to D plus 1. So a practical rule of thumb is that the VC dimension can be roughly viewed as the number of free parameters, or the number of effective free parameters. That's a rule of thumb that you can use to check some of the simpler machine learning models. Or sometimes when designing machine learning models, we design our hypothesis set such that, okay, we can estimate its VC dimension using the number of free parameters. But this is not always, okay? If you check the modern deep learning models, they may have millions of parameters and so on. But most often their VC dimension does not look like millions, or their model behavior does not look like a model with millions of VC dimension. So it is still an ongoing research direction to understand the model complexity behind modern deep learning models and so on. Okay. But before we go into the zone of deep learning, the number of free parameters is usually a pretty good rule of thumb for estimating the VC dimension. Now, remember we talked about the relationship to learning with respect to the size of the hypothesis set. Okay. Now we have our new friend, the VC dimension. Let's revisit how VC dimension relates to the two questions here. Now, previously we used the size. So we say that for small n, the bad probability is low, but we have too few choices to ensure that E-in is low enough. While for large n, there are many choices. We can ensure E-in to be low, but E-out may not be close to E-in. Now, with the concept of the VC dimension, it now plays a similar role to the original n, but maybe play it a little bit better because it calculates the effective number, effective complexity that we actually care about. When we have a small VC dimension, it's easier to guarantee that the bad probability is small. Therefore, we can have a better chance of ensuring that E-in is close to ER, or we can have a better confidence. However, it means your hypothesis set is limited. Okay, maybe it cannot shatter the data sets that you have on hand well, or it cannot produce a dichotomy that matches the label vector that you want to approximate. So therefore, E-in may be high. On the other hand, if we look at the large VC dimension, then we can ensure that E-in is small enough because your model has a better fitting power. It can produce many different kinds of dichotomies. On the other hand, the bad probability can be high, and therefore E-out can be far from E-in. Using the right VC dimension or the right hypothesis set is therefore very important. And in the future, we will discuss more about how we can select the right hypothesis set. That's the message behind VC that we want you to know about. We'll continue the discussion here because we have some follow-up message about VC that I want to wrap up before we accept more questions. Now we talk about the VC bound, and we can rephrase the VC bound in another way. Originally, we're saying the bad probability, we want the bad probability to be upper bounded. Another way of looking at this is to convert the bound to the good probability. Okay, so basically with probability higher than some tolerance, okay, we can guarantee the result to be good, meaning E in is close to E out. So basically this is just reverting the direction of the inequality. Now, what we can do here is to set this tolerance to be the upper bound here. Okay, that's what we want to guarantee. And then translate this back to the difference between an E in and E out that we can guarantee. After we set this and doing some moving of the terms and so on, we basically get this term. So this term actually means if we set a tolerance of our luckiness, of course, okay, how far can we guarantee E out and E in to be? Okay, how far can we guarantee their difference to be? So that's the tolerance that we have, or that's the price we are paying for generalization. Okay, sometimes this is called the complexity term. Now, let's look at this term. Okay, the generalization error would then be upper bounded by this square root term and so on. If you have a higher VC dimension, it's harder to guarantee generalization. And if you have a large number of examples, then eventually this generalization term complexity would be close to 0 and so on, meaning you have E in actually very close to E out. This is called the generalization bound, okay? And it tells us that E out is less than or equal to E in plus this price, okay, that we're paying in addition to E in. Actually, if you notice, there's the absolute value here, and if we decompose them, we also get another side of the inequality. Okay, but this other side is usually not that important to us because basically we want E out to be the lower the better. So we don't actually care about its lower bound, but we care about its upper bound. Its upper bound is E in, how good we're doing, and the complexity we are paying from the VC. So this later term is usually named penalty for model complexity, and we will use this big omega here to name it. It depends on three things. 1, delta, our luckiness choice. 2, n, the number of examples that we have. And 3, the hypothesis set, which reflects its property by the VC dimension. And the VC message tells us that with high probability, E out is bounded by those two terms. So choose a good hypothesis set, gather enough examples and so on, so you have a good return, and knock down your E in your learning algorithm, and you have a second term, and then you can guarantee good E out. That's what we eventually want to have. Or if we plot, okay, the relationship between the error we get and the VC dimension, the hypothesis sets that we use, we get this figure, which is arguably one of the most important figures in this class that you may want to keep in mind. When VC dimension grows, okay, basically when you use a hypothesis set of higher and higher VC dimension, what happens is that your hypothesis set becomes more and more powerful, and you are more likely to find a dichotomy that matches the data sets that you have on hand. Therefore, the in sample error, the E in decreases. Okay, that's natural. So the blue term decreases when you increase the VC dimension. However, the price you are paying for model complexity, the red term grows. So this is your omega. The blue term decrease, the red term grows. What happens to the in sample error is that it generally decreases in the beginning because you are fitting better and better. So this decrease is mainly caused by the term here. But in the end, after you have reached sufficient in-sample error, then the huge complexity you are paying may get into place, so your out-of-sample error would grow eventually. So this is the E out that you actually care about. From this, you see that we actually have an optimal VC dimension somewhere in between. This is the sweet spot that we want to reach in learning generally. How do we reach that? Shortly speaking, if you are in this region, left-hand side, you increase your VC dimension. If you are in this region, you decrease your VC dimension. It seems simple. But, of course, how do I know if I'm in the left-hand side region or right-hand side region? We don't know yet. But we will teach you some techniques that can help you select your model, tune your complexity, and so on to have a better chance of falling in this sweet spot, the right VC dimension. That's basically what we do in machine learning nowadays. Understand where we are in this very illustrative picture and try to choose a hypothesis that uses the right VC dimension to achieve decent performance. And that's what we're talking about in this figure. And it actually tells you that the most powerful hypothesis set, which is on the right-hand side, is not always good. This should distinguish you from other people who have not taken this machine learning class. People who have not taken the machine learning class would have the tendency to just use the most complicated machine learning model to solve their task. No. You should understand that this is perhaps dangerous because you are in the right-hand side and your danger is the model complexity. You should understand that you need to choose the right complexity rather than just using the most powerful hypothesis set. That's the VC message you should keep in mind. Another way to rewrite the VC bound is in terms of the sample complexity, which means we can set up some specs that we want to achieve. For example, I want my E out to at most deviates from E in by 0.1, and I want my luckiness to be 90% lucky, which means I allow 10% unlucky time for the data sets, that data collection process that I have on hand. And if I have chosen a hypothesis set with this particular VC dimension, then I can evaluate, okay, how many examples that I need to make everything behind my design spec. Okay, so given the design spec, what's the N that I can take? Now let's try. How about if I give 100 examples to my learning problem? Would I reach my spec? If you throw 100 into this, you basically get this particular value to be 2 times 10 to the 7th degree, which is far from 0.1. No, it's not less than or equal to 0.1. That means you do not have enough examples. 100 examples, not enough. Let's try 1,000. Oh, even worse. You get 9 times 10 to the 9th degree and so on. Even worse, it's not less than or equal to 0.1, not less than or equal to your delta. Why is that? Because you actually have a term with respect to n that grows pretty rapidly with your number of examples as well. So sometimes you get very unreasonable bounds. This is bad probability. You want this probability to be small. You want it to be less than 1. You want it to be less than or equal to 0.1 according to your spec. But now you cannot achieve it with 1,000 examples. How about 10,000? Okay, still not too good. How about 100,000? Oh, you get some value that's decent. Actually, because of the exponentially decreasing, you get a value that's very, very, very small, but perhaps too small for your design spec. What's the smallest n that you get? If you really play with all the different n and so on, you would see that if you use around 30,000 examples, you will get the best probability to finally follow your spec very tightly. And this is called the simple complexity. So basically, by having this spec, we need this number of examples to achieve the spec. Now, this seems to suggest, okay, if you actually do some approximation analysis, you can get that you need n to be around 10,000 VC dimension to get decent learning performance, to get decent generalization performance, actually. Okay, but if you think about this, 3-dimensional, that's the 2D perceptron we encounter. How many examples do you need me to give you on 2D to achieve decent learning with perceptron learning algorithm? Perhaps 20, 30, 50. You really, really, really do not need 30,000. Okay, so 30,000 is good. It's suggested by theory, but it's totally not necessary, physically not necessary in practice. The practical rule of thumb is that 10 VC dimension is often enough. Okay, in the particular 2D perceptron case, if I give you 30 examples, that's really enough. 100 examples, that's luxurious. You don't need 30,000. So combining this with what we talked about previously, if you know that your learning model has some number of free parameters that you can tune, especially for the more traditional learning models, multiply it by 10. That's the number of examples you need to gather for decent learning performance, because this number of free parameters is often a good estimate of the VC dimension. Multiplied by 10, you get the number of examples you need for starting your machine learning task to ensure somewhat good generalization. And this result hints us that the VC bound itself is actually loose. Okay, it's not as good as we want for practice, because in theory, you need number of examples close to 10,000 VC dimensions. Now, practically, you need probably 10. Why is it loose? Because when we derived the VC bound, although we didn't show you the details, you have seen that we used a bunch of approximations that makes the math go through and makes the bound flexible enough. In terms of flexible enough, for example, we don't need to know E out. Okay, whether E out is close to 0.4 or close to 0.01, we use the same Hofding bound, which is by itself loose, but it allows the VC dimension to cover any distribution, any target function without knowing them. We use the growth function instead of the number of dichotomies that's produced on arbitrary inputs. And it allows us to provide the worst case analysis on any data. Okay, it's not the particular data that we have on N, but any possible data. The lucky ones, the unlucky ones, and so on. We cover all of them by the growth function. And actually, we summarize the growth function with the VC dimension. Okay, so it allows us not to look at the details of the hypothesis set as long as we can have its VC dimension as the summary number. And we have union bound on the worst cases. it essentially removes what our algorithm is doing. Our algorithm can pick any hypothesis in the hypothesis set without knowing whether it falls into the bad zone or not, okay, while we can always have the guarantee. So those are many any's here, okay? Any target, any data, any hypothesis set, any algorithm that we use, this allows us to get the VC bound, which is why it's loose, okay? If we specifically know our algorithm, know our hypothesis set in detail, know the data or data distribution we're going to encounter, know the target function that we're considering, maybe we can do better. But if we insist on all of them to be any or can be unknown in some sense, then VC bound is it's very hard to improve the VC bound. Okay. And also, although VC bound is loose, it's often similarly loose for all the models that we're considering there. So it can be still used for qualitative comparison, maybe not quantitative. Maybe you don't want to actually throw in the numbers to the VC bound and get that the bad probability is less than or equal to 10 to the 8 or 10 to the 9 or something. But you can still use the VC bound to qualitatively say, your VC dimension is lower, my VC dimension is higher, so we should do some sort of selection and so on to make sure that we're doing the right thing in machine learning. That is, we're teaching you the VC bound for its philosophical message, not for quantitative evaluation. And those philosophical message, as you will see later, will be important for improving machine learning. Okay, that's about all VC bound that I want to talk about. Let me quickly summarize this part, which actually should be finished last time, but most often we are delayed in course schedule and so on. Okay, so we started with the effective number of lines and then extended to the hypothesis, okay, in the last lecture, which tells us the growth function, okay, that can be used to model any hypothesis set. From the growth function, we discussed an important concept called the breakpoint, okay, which means a point that we cannot shatter any set of input vectors with that number, and use the breakpoint to define the VC dimension as a very important property of the hypothesis set. We analyzed the VC dimension of perceptrons today, which allows us to complete the perceptron story that we can do good learning with the perceptrons, of course, if the dataset is linearly separable and if we have enough examples. We say that the physical intuition of VC dimension is the model complexity that we need to pay, and in turn tells us the simple complexity, the number of examples we need to prefer if we want to use a particular hypothesis set. Okay, and this interpretation tells us, okay, that VC dimension, the philosophical message behind the VC dimension, can be helpful. That's the most important theoretical and philosophical parts that we're going to teach in this lecture. And next we'll move on to the algorithms and so on. But before we do that, let me check whether we have questions on Slido. Okay. Let's see. How can VC dimension represent the hypothesis power? VC dimension is the maximum number of examples that can be shattered. Okay, and therefore, when you can shatter more examples, you can imagine that your hypothesis set is more powerful. It can do more things. Shatter is something a hypothesis set can do, okay, can fit, okay, the dichotomies and so on. So you can think of shatterness as evaluating the fitting power of the hypothesis set, and VC dimension is just a summarization of shatterness and therefore represents the power as well. In theory, we need 10,000. In practice, we require 10. Can the professor put the reason? Okay, for the practical parts, really, there's no reason. Okay, and this is more like our experience, our physical experience, and so on. Well, we explain the reason why the theory is so loose. Okay, in the lecture, being the VC bound is used to guarantee arbitrary condition, while in practice we're not facing arbitrary conditions. We're facing the condition we're interested in, and often those conditions might be simple. Okay, so that's philosophically, some people say that the problems that can be solved by machine learning are relatively simpler ones within all possible problems in the world, or all possible problems that God can come up with. And so we are not dealing with every problem, okay, which is what the VC bound tries to guarantee in the worst case. We're dealing with the easier problems, so we can expect the bound to be not so bad in a sense. That's can possibly explain what we have observed here in practice. And the bound on page 46 can be bigger than 1. Yes, okay, that's definitely what you can see in the VC there. Okay, this value, if you put a very small n and so on, can actually give you something bigger than 1, which is of course nonsense, or the bound is not that reasonable, and we use this to actually illustrate the looseness, okay, of the VC bound. The VC bound looks good. It's tight only if you have a super large number of examples, and in many of the practical design factors that you encounter, for example, small epsilon, small delta, reasonable n, and so on, the bound may not be that meaningful. Can I take the derivative of ER curve to get the best VC dimension? That's a very interesting thought. Several things here. First, that particular curve is not analytically calculated, and in practice, you only have some points on that curve, so you do not know whether what that curve looks like, or it would be hard to actually take the derivative, okay? Because usually to take the derivative, you need to know the analytical form of the curve, while in practice, you usually do not know that. So that curve is more conceptual than actual. On the other hand, you can actually do something, okay, by having that curve in mind, like finite difference or something, in order to get to a better position of the ER curve. That's possible, okay, using finite difference. So that's similar to the take derivative idea, but more practical. That's one thing. Another thing about E out being not analytical is that E out is typically unknown. When you have an unknown curve, then not only you cannot take the derivative, but it's very hard to know where the lowest point really is. That's the challenge that we will need to face a little bit later. Where does the 10 DVC result come from? Me. Okay, okay, I not just me. Okay, but if you, I don't know, maybe if you check the learning from data book, we list something similar inside the book too. But generally, me actually means it's experience, it's human learning, not machine learning. Okay, it's human learning saying, okay, in my years of experience in the academia and in industry, if I have a learning model with VC dimension equal to 20, and then at best start preparing 200 examples to get started with. No guarantee. Okay, this heuristic is given you as is. Okay, and of course you can experience in the future by yourself. But on the other hand, following this question, I actually want to add that another concept that is important is if you have 200 examples on hand, you should perhaps consider a machine learning model with around 20 VC dimension. You set your model complexity according to the data you have. That's also a good practice, because if you have 200 examples, but you give it a model with 100,000 VC dimension, it's doomed to fail in some sense. Okay, so this particular rule of thumb has two possible meanings. You want a particular model with some VC dimension, gather 10 times more data. You have some fixed size data, consider limiting your VC dimension to be 1/10 of your data. Okay, those are good rule of thumb that you can use in practice. Can I borrow a textbook from teacher if I really need the textbook for learning? Certainly. Okay, in our very first lecture, there are two things that we mentioned. First, we have shared copies in the library. We have shared copies in my lab that you can go read the book there. And if you really need the book but cannot afford it, send me an email and I'll see how I can help. That's the what we can do in there. Okay, why is the actual n and the or the practical n and the theoretical n so different? Okay, does it mean that the theory is meaningless? Short answer: yes, the theory is meaningless in terms of quantitative evaluation. And we explain why the bound is loose and so on. So in terms of quantitative evaluation, it's correct, meaningless, and we explain the reason of the looseness. On the other hand, being meaningless in terms of quantitative evaluation does not mean we cannot use the bound or the philosophical message qualitatively. And that's what we're going to do with the VC bound. So in the future lectures, you won't see me actually calculating the exact values of the VC bound. That's meaningless. But I'll discuss why VC bound can help us understand this algorithm design and so on. That's meaningful. Okay, and that's what we will encounter in the future. But each experiment may have different initial weight. We need running the same model many times. I'm not fully sure what you mean by different experiments here, because in the lectures that we encounter today, we're not talking about experiments yet. Assuming that you may be talking about perceptron learning algorithm, which is a randomized algorithm. Yeah, running the model for different times may give you different weight vectors and so on. They are similarly guaranteed by the VC bound. Okay, so you can say that all the weight vectors that you obtain by the perceptron learning algorithm is equally good or equally bad. Whether we can differentiate them will be a later topic that we will discuss in future classes. Okay, great. Let me switch to. Sorry about that. Sorry about that. I just accidentally dropped my microphone. It seems to be still working now, but I assume you heard some noise and so on. My apologies. Okay. Now let's see what I'm going to teach here. Bear with me for a few minutes. Actually, let's do the following. It's very close to the rest time anyway, and for smoothness of teaching, let's take a 10-minute break, and I'll use the 10-minute break time to switch the slides and so on to prepare for the next parts, and then we can be back with a more smooth lecture. So let's take a 10-minute break. Thank you. Okay, welcome back. And let's move on to the linear models that we're going to discuss here. But before we do that, I saw two questions on Slido. Let me quickly answer them first. First is actually the two questions are both about separability. Okay, in general, we do not always encounter linear separable data sets in practice. Okay, that's for sure. And in the future, we'll see whether we actually insist on separability. I mean, okay, whether linear or nonlinear, whether we'll insist on being separable or we just throw the whole concept away and say that, maybe there are a few points that are just noise and so on. We don't need to separate everything perfectly. Okay, that's something we will talk about in future classes. But the VC bound results that we have discussed actually apply to all cases. Okay, we are just talking about VC dimension. Okay, that's the property of the hypothesis set we need to use. Whether the data is separable by the hypothesis set or not does not make any difference to us. And therefore, the results that n needs to be around 10,000 VC dimension applies to linear hypothesis set or nonlinear hypothesis set, okay, regardless of the separability of the data sets. Okay, that's something we want to clarify here. Okay, let's move to what we're going to teach today. Okay, now enough with the theory. Now we're starting talking about how can the machines learn, in particular extending the linear models that we have seen. The perceptron is one particular linear model to other cases. The first problem that we're going to encounter is a variation of the credit approval problem that we have seen. In the credit approval problem, we use the application profile to decide whether to give the particular applicant a credit card or not. Now consider another problem where we are trying to decide the credit limits, okay, that we're going to give for each applicant. So the credit limits is a real value instead of a binary decision. Now the same flow of learning that we have encountered can be applied here, and the only difference is that the output space is now a real value, actually a non-negative real value maybe, and that's the regression problem that we have discussed in earlier lectures. How do we solve this problem? Following the perceptron model that we have seen, one way of solving this is to represent each applicant as a vector feature x, okay, that's we are now very familiar with, adding our usual x0, and then we ask the machine to approximate the desired credit limit with a weighted sum. So the weighted sum can mean how important each factor is in terms of getting into the credit limit approximation. Okay, so we want the y, okay, the desired credit limits that we want to output to be close to a linear combination of those feature vectors, and the combination weights are our good friend w here that we want the machine to learn. That is, we can represent each hypothesis set that we're going to consider as a linear combination, which can be simply represented by an inner product here. If you check the formula of those hypotheses here, you will see that it is like a perceptron, but without the sign. Okay, we take the sign in our perceptron learning model because we want the hypothesis to either output +1 or -1. Now that our hypothesis would output a real value, okay, we don't need the sign there. Okay, so this can be think about a more flexible version of the perceptron without the sign. Visually, what we're going to do is something like this. For example, let's say we have a one-dimensional data set, okay, and we want to fit the corresponding values on each example. So this is a particular x1, y1, this is a particular x2, y2, and so on. We feed the machine with this data set, all the circles there, and want the machine to learn which blue line best approximates this example. Actually, you have encountered this maybe in your high school math. Okay, draw a particular line that matches those examples the best. What are the parameters of these lines? In your high school math, it tells you that there are two parameters. One possibly being the intercept, and the other possibly being the slope. Okay, so in high school, you try to calculate this line by finding the optimal intercept and slope. In our terminology, we find this particular line will be having some W that basically says the output is W0 plus W1x. Okay, so this is the equation of the line. Okay, we're learning this equation, and from this equation, you can actually see where the intercept is, where the slope is. Okay, so we're just changing the terminology here. We are learning W0, we're learning W1. They have a physical meaning of corresponding to the intercept and the slope. That's in one-dimensional inputs. Okay, our input is one-dimensional. We plot the label in another dimension to help you understand the process. Now, if we have two-dimensional data, okay, then the visualization will be something like this, where we now learn a plan, okay, that describes those data the best. Okay, and those plans can be described by three values. One, again, the intercept, okay, somewhere here, and two, the directions that you want the plan to have on the first axis and the second axis. And the good thing about using general vector notation is similar to the perceptron case, we can kind of remove the dependence on the dimension. The same algorithm works for 1 dimension, 2 dimension, 3 dimension, 1, 1, 2, 6 dimension, and so on. And this particular learning problem is called linear regression. Okay, in lower dimensional space, we try to find lines or plans to fit the data, and by fitting the data, we actually mean we want the line or the plan to have small residuals. And residuals are differences between the prediction, which is here, and the actual data value. So this part is the residual. If we predict 1.6 while the actual value we want is 2, then there's a residual of 0.4. We want small residuals. Now, previously we talked about how to evaluate machine learning algorithms, but surrounding the concept of binary classification. Now let's put this more generally. The way we evaluated our hypothesis was based on calculating whether G is the same as F. That's for binary classification or classification in general. And that can be generalized to an arbitrary function that we call ERR here. So this ERR basically takes two values. One, our prediction G, the other, our goal f of x, or the y, the label there, and try to compute their difference. And the E out notation that we were familiar with is simply an average of this ERR over the distribution that we are considering. And this ERR is called a pointwise error measure because it evaluates the performance difference between G and F on a single example. And we average them over the whole distribution that we're interested in. Following this definition, we can extend machine learning to arbitrary problems with pointwise error measure by having a corresponding in-sample error that's basically defined as all the values, okay, all the ERR evaluated on the examples. That's the prediction. That's our desired label, or more generally, YN here. And when things are out of sample, we average them over the distribution. So we can extend the E in, the E out that we have seen to arbitrary ERR, not just the original one that we considered. And we will mainly consider pointwise error functions for simplicity in throughout this whole class. So that extends our learning picture a bit by having ERR for designing our algorithm. Okay, so we let our algorithm know the error measure that we're interested in. If we're doing binary classification, we should use a binary classification algorithm. If we are doing regression, that like what we will discuss, our algorithm would know the ERR, and we use this particular error function, error measure, to evaluate our final hypothesis. And the good news is that extended VC theory, or the philosophy that we discussed, works for most of the hypothesis set. I mean, even for regression, for multi-class, for whatever, and most of the error function that we're going to consider. Of course, there may be assumptions on some smoothness and so on that we're not going into detail here. But generally, okay, we don't need to show you the VC proof all over again. We just tell you that you can believe that the same philosophy where we try to constrain our hypothesis set and use some well-behaved error measure, then we can expect EC to work. We can guarantee that E out is close to E in, and we can focus on minimizing E in. Now, there are two important pointwise error measures. One is what we have encountered, usually called the 0-1 error. 0-1 because the error function only outputs two values, 0 or 1. 1 meaning error, 0 meaning no error or correct. Okay, so basically this error function, if we shorthand it as y delta, meaning for prediction, and y meaning our goal value, this error function just computes the difference and is often used for classification. And the error function that we'll encounter next is called the square error, basically computing the difference and then square to make things positive and so on. And it basically computes how far y delta, the prediction, is from the actual y that we want to have. And it's often used for regression, for comparing two real values. And square error is what we will use to quantify small residual. Remember, for each line or each hyperplane, we can compute its residuals and so on. Then those residuals are basically the difference that we see there, okay? And the square of those residuals are what we are going to use to measure how good the hyperplane is, how good the W is. And square measure for regression is a popular and historical error measure for linear regression. It's in-sample error. It's just, okay, I'm writing down the formula for in-sample error. We have square error here. We have the prediction, which we have formed the prediction to be just the inner product without taking the sign. So we can say this is E in of H, but because each H is actually parameterized by a W vector, we can also say this is just E in of W. And out-sample error, again, parameterized by W, would be just computing this value, compare it to whatever Y that we have in our distribution, in our test set, and then average over them. Now, if you believe the VC philosophy that I talked about, then after forming this problem, we have the in-sample error. We want our out-of-sample error to be low. What's the next step? The next step is to minimize E in. If you minimize E in and you believe the VC story, then you would minimize E out, which means you would, on average, get a hyperplane parameterized by W that has a small residual square. Okay, so that would be the good hyperplane, the good line that we want to have. Now, that's the linear regression, the motivation of linear regression, the basic setup that we want to talk about. Let's see if we have this question, okay? Why do we need x0 in regression problem? Okay, that's a very good point. There are two things you can think about. Okay, one is its historical reason. Okay, historically, for example, we want to fit a line. We say we have two parameters, slope and intercept. x0 and the corresponding w0 would mean the intercept. So if you don't have x0, that's fine, but it means you are fitting a line without an intercept, which can be useful for some applications, but in general, the intercept may help you model the problem better. Why is that? Because in some cases, the intercept can mean a very basic physical quantity called the average of the value that you want to output. The intercept is not always equal to the average, but it can tell you some trends about what your data look like, even without considering other feature vectors. Or put it this way, okay? If you feed your fitted line with a all zero vector except x0, then you get the intercept, and that can tell you something about the nature of your data. Okay, so in cases where, for example, you want your machine to output a stock value, and the stock value is commonly around 100, regardless of the day or the time or other quantities that you put in, then maybe having an intercept or having an x0 and corresponding w0 in your formula help the machine capture this zeroth effect. Okay, meaning the stock value is often around 100 more easily, because the machine can just put 100 as the w0 there and get a good prediction. How do we choose between the squared error and the absolute error? Okay, that's a good question. In terms of evaluating the difference between two values, you can take the absolute value, you can take the square value, you can take the difference to degree 1126, and so on. Different formulas have their different effects on the algorithm. The reason that we're choosing squared error here, as you will see next, is that its corresponding E-in is relatively much easier to optimize than the absolute error. Okay, while it is totally possible to optimize the absolute error if you are willing to design a good machine learning algorithm. So the choice is more like friendliness, okay, in helping optimization. Of course, okay, there are properties of square error that you may not want. You'll actually see some of them in your homework too. Stay tuned. And you may want to change your error function and so on. That's a big topic by itself. And if you check the statistics literature, there's actually one direction called robust statistics that discusses what different error function means in terms of their statistical properties and also their algorithmic properties. Okay, great. Now let's check the next part. Okay, so our next task, optimize E-in. How do we do that? We have the formula for E-in. It's an unconstrained optimization problem. If you know how to write down a multi-variable optimization problem to whatever solver you can want, that's it. Okay, but for people who are not familiar with optimization solvers yet, it may seem that this equation, there's summation like a for loop, there's square and so on, is too hard to solve. So let's try to simplify it a bit, okay, and particularly with our knowledge in linear algebra, so the problem would look more easily solvable. What we're going to do, okay, is to organize those terms to a matrix form that help us look at the equations more cleanly. Before we do that, let me first put a very small modification that swaps the order of the inner product W transpose X to Xn transpose W. This is simply for making the math look a little bit easier, and you know that inner products is just exchangeable. Okay, so after switching, what we can do is to write down the values that we're interested in and replace the summation of something squared as a vector square, the length of the vector square. What do I mean? If I have this vector having each component being what I want to put in here, if I have each component in here, and then computing this vector's length square, that's exactly the summation squared that I want to have on the top. So nothing too special, I just write down x1 transpose W, x1 transpose W, and then there's minus y1. Okay, that's the first component I want to put in here. And there's minus y2, blah, 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 until minus yn. There's x2 transpose, there's xn transpose, and there's w, w, w. Okay, so I'm just writing down things by definition. After writing this down by definition, representing this as a vector allows us to further decompose the whole thing into a matrix form. Let's gather the similar things. We have w, 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 w in every component multiplied by x transpose. So I need to have a matrix of x1 transpose, x2 transpose, blah, 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 xn transpose to gather those red terms. And then I can have y1, y2, blah, 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 yn to gather those purple terms. Having those two, okay, what's this? What's this red guy? This red guy is a matrix with the input vectors as its rows. In our terminology, this is just the X matrix. The X matrix we have used to prove for the perceptron learning algorithm. And I'm going to name this vector that contains all the y's that we're interested in, the y vector. So now I can put things in a more clean way, saying, the inner part is just a matrix, the X matrix with all the input vectors as its rows, and multiplied by W, the hyperplane I'm interested in, minus the Y vector that's within my data as well, and then taking this vector squared, that's the E in that I want to get, of course, divided by N. And you can check the dimension of those matrices and vectors to make sure that we are on the right track. Okay, now there's minimize E in, and we have written it down to the matrix form. Now this E in is a continuous differentiable and usually called a convex function of W. Okay, now our W is a vector, so it's a little bit hard to imagine in a multi-dimensional space. And basically, convex means the shape of the curve that we want to optimize, this particular shape, this particular curve is valley shaped. Okay, so basically this valley shaped curve would contain some minimum point somewhere. Okay, that's what we want to get. Now, for this kind of valley shaped curve, this convex, okay, if you really don't know what convex means, that should be fine for this class. Okay, but what you can see here is for this curve, the minimum point, okay, the point we want to get because we're minimizing it in. The minimum point would satisfy something, some necessary condition here, which is at the bottom of the curve, at the bottom of the valley, the gradient, which tells us which direction we can increase the function value, would be 0. Okay, so this is a smooth function, a differentiable function, and its minimum point must satisfy this. Okay, and physically, it means if you put a ball at that point, it cannot be further rolling down anywhere. Okay, because surrounding that ball, there's nowhere to get higher or get lower. So our task here is to find this particular W such that the gradient equals 0. If we can find that particular W, that must be the W that minimizes this E in. And I'm going to name this particular W, WLIN. And this LIN is not named after me. Okay, although my last name is Lin, this LIN is not named after me. It means linear. I'm going to get some linear weights or linear regression weights, and the property of this linear regression weight is that it needs to have gradient equal to 0. Now, how do we calculate this gradient of W? Okay, gradient of E in. Sorry, gradient of E in. We can again expand the metric form that we have get with math we have learned in our linear algebra class. So expanding this, we would have a quadratic term, and the coefficient of the quadratic term is basically x transpose x. Okay, that's like this first term expanded by a square. And there's a last term, y transpose y. That's a square term expanded here. And there are other terms, okay, that's basically the cross term between those two. And if we write this down, we will have x transpose y, okay, that's the coefficient of the middle term. So again, that's just linear algebra that you should have learned before this class. And how do we get the gradient? We're not going into the math details here. Actually, you should have completed the math details in your homework 0. Remember, we say if you don't do homework 0, many of the results would come back and haunt you. That's one part. In your homework 0, you actually have one problem that helps you compute the gradient. We will take the results from there, but I want to tell you just some physical intuition that you can build from your high school math. I'm going to name this matrix A, this inner coefficient B, and this final value C. Remember, if you have just one W, then the function above is just a quadratic function that you should learn how to optimize in your high school class. How do you optimize? Well, you can compute the differential with that single variable function and so on. You get the gradient. That's simple. 1W, that's simple. And now you have a vector W that we're going to use here, and the math is similarly simple. We're taking the fact that A is a symmetric matrix, and gradient just have a similar form, okay, of compared to the one variable case. You can do the math, you can do the actual math by definition and so on, like what you do in your homework 0. But for now, we'll just take this result and use this to derive the linear regression algorithm. So substituting everything in, we have the gradient being 2 over n. And then here, the coefficient behind W is x transpose x, and the coefficient in the constant term without W is x transpose y. Now, the question is, we want that to be 0. We want to find some W such that this is 0. This is what? This is just degree 1 linear equation, a linear equation that you want to solve. Okay? 如果中文的话，一次方程式 linear equation, solving linear equations. You know that solving linear equations is not that hard if the matrix here, x transpose x, is invertible. If it is invertible, all you need to do is to multiply the inversion to the other value, and then you get the solution. We have seen this. Okay, multiply the inversion when we prove the correctness. The VC bound of perceptrons. Right? Multiply the inversion to the value you want to get. The W that you get would satisfy your needs when inversion exists. Now, in your homework, you are going to prove that there's a particular name for this, okay, when things are invertible. X transpose X inverse X transpose, okay? And this particular term is usually denoted as dagger, okay? So this dagger is like a sword, okay, and called the pseudo inverse. Most often in practice, X transpose X is invertible, okay, and this is because this particular X transpose X matrix is D plus 1 by D plus 1. So we need its rank to be D plus 1 to be invertible, while the original X matrix has multiple examples, multiple rows that are often much bigger than D plus 1. Why is that? D plus 1 VC dimension wants the machine to learn well, many examples. So in practice, okay, most often you have enough examples such that X transpose X is invertible. But of course, there are cases where you cannot guarantee an invertible X transpose X. In that case, it means your linear system, the linear system you're trying to solve above, is it does not have one optimal solution. It may have multiple optimal solutions. And in that case, you can define the pseudo inverse, okay, the X dagger, in other ways that we will guide you to do in homework 2. Actually, you have encountered that in homework 0 as well, but you didn't know it. We will guide you to do that in homework 2, so you understand it a little bit better. Now, in any case, okay, you can get an optimal solution that minimizes E in by setting the gradient to 0. In practice, we often suggest you to use well-implemented routine for the pseudo inverse. Instead of directly computing the X transpose X inversion and then multiply by another matrix by yourself, because you know that all those algorithms are numerical algorithms, meaning they process floating point values and so on. And sometimes it needs special care to ensure that the numerical results produced are of enough stability. Okay, and therefore, often, okay, if you can access a routine with good pseudo inverse, use that. Okay, and we derive the math here for the invertible case simply for your reference. Now, this leads us to the linear regression algorithm. You have a data set, and from the data set, you can construct two matrices, or one matrix and one vector, the input matrix and the output vector. Then you can compute the pseudo inverse from the X matrix, and then get your resulting linear weights. Okay, the best hyperplane, the weights that represents the best hyperplane by X dagger, the pseudo inverse, multiplied by Y. And this is a simple and efficient algorithm with a good routine for calculating the pseudo inverse. That's the linear regression algorithm. And we are specifying the linear regression algorithm in a matrix form. And if you look at, some of you may have encountered this in your high school math, called least square algorithm, 最小平方法. Okay, and in those cases, you may be dealing with one value, one parameter or two parameters, solving simple equations and so on. Now we're generalizing this to the vector case. Now, every year when we teach linear regression, one of the things that we often encounter is that it doesn't look like a learning algorithm. Why is that? Because essentially we are kind of just computing some matrices and then use matrix multiplication and so on. Boom, we get our WLIM. And that kind of closed form solution, that kind of instantaneous solution, does not look like learning. Okay, it looks like some computing tasks that you use to solve. For example, if you are computing the average, okay, of a bunch of numbers, you write a for loop to compute that, boom, you get the solution. It doesn't look like learning. And it is not clear whether we're improving E in nor E out or E out iteratively. Okay, meaning we're just doing one step. There's no iteration. We're not gradually improving or eventually improving like PLA. But if you think about it, the answer may also be yes. We have good E in by this algorithm. It's optimal as we showed in the previous slide. And can we guarantee good E out? Yes, because, okay, you can actually derive from the theoretical results that the hypothesis used by linear regression has finite VC dimensions just like perceptrons. Okay, so we can guarantee good E out. And if there's good E out, then we have learned something, or the machine has learned something. And how about improving iteratively? There may be iterative improvements or changes. It's hidden in the routine that calculates the pseudo inverse that you don't know. Okay, for example, there may be routines like Gaussian elimination and so on for computing the inverse, and those routines are doing things iteratively. So maybe the answer is yes. And the general message that I want to show you here is that if the E out is good, then learning should have happened, regardless how we do learning. Okay, some people do learning rather iteratively, reading things, improving one by one, and so on. Some people lock themselves in a room and then boom, they learn everything. So maybe learning doesn't have to be iterative. We can just judge by the final result, like some professors judging you by the exams and so on. What's the theoretical guarantee that we can get for linear regression? We're skipping the proof this year, but I want to show you this curve. This basically tells us the number of examples versus the error that we can get from the linear regression algorithm. Okay, so it is like in a setting, in a particular data generation setting, how does E in and E out vary, okay, with respect to the number of examples that we have on hand. Note that I'm using E in bar here and E out bar here, okay, meaning the results are averaged over the generation process. I'm not going to explain the details here. And after some derivation, what we can basically get is that E out is a little bit more than the natural noise level within the data. How much more? D plus 1 by n, where n is the number of examples and d plus 1 is the dimension of the data that you have on hand. On the other hand, E in is a bit lower than the noise level, meaning it's 1 minus d plus 1 by n. So if you plot it into curves here, the curve for E in is basically growing to the noise level, and the curve of E out is decreasing to the noise level as you get more and more examples. And the difference in between, 2d plus 1 divided by n, that's a message that's similar to VC. VC says we need to pay for a complexity price. What's the complexity price? Something related to the VC dimension, which is d plus 1 here, and something related to the number of examples, which is big N here. If you get more and more examples, you would make the gap smaller and smaller, and the gap is the generalization error that we generally need to pay for learning. And this kind of curve where we have one axis being the number of examples and the other axis being the error is called the learning curve. Okay, it tells us how good our learning algorithm is when we get more and more examples. Now in linear regression, because we have this proof, we have this result, we can actually show that learning happened. Okay, of course, in terms of procedure, it is not totally clear whether we're doing things iteratively and so on, but at least in the end, in terms of the final exam, in terms of E-out, if we have enough examples, learning happened. We reached the best, or we are close to the best error that we can get. Okay, questions about linear regression? Why we have finite VC dimension in regression problem? Okay, it's not as easy as it sounds, but generally, let me say this. If you define the VC dimension in some other ways, it's not exactly the same as how we define dichotomy, blah, 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 and so on. You can extend the concept of VC dimension to the regression problem, and then we can prove that linear regression hypothesis set has finite VC dimension too. But that requires defining the VC dimension in another way, which will be too complicated for this class, and we're not doing this. So we won't have to prove the learning curve of linear regression in the future homework? No. Yay. Okay. That's something good. Okay, we decide to skip the proof of linear regression because we believe it's a bit too much to introduce you with much more theory in this class, and therefore we remove that from the lecture and we remove that from the homework too. And there's a particular problem in Chinese. Okay, if the data is normalized, okay, do we not need W0 because, okay, maybe after normalization, the intercept can be close to 0 or the intercept part can be absorbed by the normalization coefficients. Let me say this, maybe. Okay, and the reason of saying maybe, okay, is it actually depends on the normalization you use. Okay, and sometimes even after normalization, some people prefer to always include a threshold or an intercept there just for, I mean, it's a small price that's we're paying for much more flexibility. Okay, so some people prefer that, okay, but indeed, what you're saying that normalization removes the, for example, averaging, the natural averaging and so on. So we may not need the W0 term as seriously as before. That's true. Okay, but in practice, some people still include W0 even if they do normalization. Page 10, okay, how do we derive the length square from the square summation? Okay, let's see, page 10. Okay, and basically in page 10, we say that every component of the vector is just the one, okay, every component of the vector, component 1, component 2, up to component n, is just the one we put in this dimension. And now, remember, the length of the vector is the sum of component square. Okay, length square of a vector is the sum of component square, and we're just using that result. Okay, so it's just plain math, okay, for vector operation. It seems that if we get weight and y can calculate x, so can we steal other people's data sets? Okay, that's a very interesting thought about whether we can calculate x from w and y. If you think about it, maybe we cannot calculate x from w and y, because at least not fully, because w is a vector. Okay, so you have d plus 1 values. Y is a vector, you have n values and so on, but you're trying to reconstruct a very big matrix that's n to d plus 1. Okay, so physically there will be multiple x that leads to the same w and y, even for linear regression. Okay, so if you look at the linear regression result, to actually get x from w and y, even if you assume that x is invertible, you have w, you have y, but now you have multiple unknowns to reconstruct. It may not be always easy. But in general, for machine learning, there are some algorithms that have the property of memorizing some of the x or some of the y. That can be problematic for some privacy-preserving applications, and therefore it's a hot research topic to design machine learning algorithms that are provably free or somewhat free from reconstructing the original data. So back to your question, in terms of linear regression, I don't think it's easy to reconstruct the x, okay? Simply because you have too few knowns and too many unknowns. Okay? But in general, for machine learning, is it possible to reconstruct the data? Possible for some models, and it's an active research direction to prevent that. Basically, when we are choosing an algorithm, do we know the VC dimension before implementing? That's a very good question. Usually, we don't know the exact VC dimension. And the exact VC dimension is often hard to prove, as you will witness in your homework too. Ha 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 ha. Okay, so we don't know. We don't know how to compute. But we can estimate. That's one thing, or we can have a sense. Okay, I'm not even saying estimate. I'm saying we can have a sense. Okay, saying when we use more parameters, we are charging ourselves with more VC dimension and so on. That's what we often do. Okay, we don't know the exact number. We can have a sense through the effective number of free parameters and so on, and we can use this sense to guide our design or guide our choice. That's what we do in practice. Okay, great. We are done with linear regression here. Let's move on to our next topic. Now I'm super worried that we are being extremely slow. Let's see. We encountered the linear regression problem and its associated algorithm. Now I'm going to introduce you another learning problem that we can solve with the linear models by some variation. And this problem is going to help us connect back to the cases for binary classification as well. Now let's consider the binary classification case that we discussed, where we want to predict whether a patient has a heart disease or not. Okay, so we're moving from the credit card example to a hospital example where we're trying to predict whether the patient has a heart disease from the profile, the medical profile of that patient. Now, when we see this, okay, we see, okay, this is a binary classification problem. Typically, maybe it comes with noise and so on. Let's try to use machine learning to solve that. We don't know yet how to solve binary classification with noise, okay, but let's imagine we have an algorithm for that. Now, let's change the problem a bit. Sometimes we do not want to know exactly whether the patient has a heart disease, but we may want to know a problem different, where we are predicting whether the patient has some chance of, or has some risk of getting a heart attack, let's say in the next 3 years. So we're predicting a probability. We're predicting the probability or uncertainty or whatever you call it that the patient can have a heart attack. This is a little bit similar to the regression problem, but not exactly the same as typical more wide range regression, because we're predicting a probability which falls between the value of 0 and 1. Also, this predicted probability could be somewhat related to the probability that's used to generate the training examples on hand. Let's revisit the binary classification case. We assume that we have generated the data by some probability on x and probability on y given x. For some x, we say there's heart attack. Some x, we say there's no heart attack, and so on. So we may have some binary classification data on hand, and if we want to just get a binary classifier, you can see that our ideal binary classifier is whether this probability is greater than half or not. And that's what we want to estimate in typical binary classification. We want to get right or wrong. How do we get right or wrong with respect to the distribution that generates the data? Well, the optimal prediction is positive 1, while the other cases, for example, if for some patients there's a probability 80% with a heart attack or with a heart disease, then the other 20% is just noise, it's just error. Okay, now, if we still get the same data, but our target function is the probability distribution itself, which actually means we're going to generate a soft value for the prediction instead of the hard value we get in binary classification. How do we do that? Okay, that's the problem we're going to study next. We get the same data that we have for binary classification, but now we want the classifier to output a soft value that represents a different target function. The previous target function, whether the probability is greater than half or not, the current target function, directly the probability distribution that have generated the data. That's what we are going to do. Now for this problem, the ideal data that we want to get is x1 and then the corresponding soft value. Right? Assume God wants to give me a data set. I'll pray to God, come on, give me this data set, then I can just learn this target functions through some sort of regression and so on and get my machine learning performance. Okay, so I need to have a softly labeled data set on hand. But most often in practice, we don't have a softly labeled data set on hand, but we have some data, some noisy data generated from the distribution. That is, I get a binary classification data set on hand. All the data is labeled circle or cross the hard labels, but I want to predict a soft output. So hard labels, positive 1 or negative 1. Soft outputs, those probability values between 0 and 1. That's what we're going to deal with here. Okay, starting from this data, this kind of data, which is assumed to be generated from the distribution. Note that this particular distribution, for example, you see this is of value 0.9 and we can get positive 1. That's with a high probability. This is of 0.2, so we can more easily get a negative 1. That's fine. But it is also possible that there's a probability 0.6 of getting a positive 1 while we get a negative 1. That's possible. That's just flipping a coin. So anything is possible as long as there's probability. That's why we call this dataset noisy. It's not only deviates from the soft values, it's discrete values rather than continuous ones. So there's deviation. And also, even the label itself, the hard label itself, is not totally indicative of the goodness in terms of the soft labels. And this is what we're going to do next. And we're going to assume a binary classification data set, but for simplicity and also to match what we have in there, we will basically sometimes have a little bit relabeling of the values we have here. There's 1 indicating we get a circle from the distribution, and there's 0 meaning we get a cross from the distribution. We use negative 1, for a cross label. But when we're saying we sample something from our distribution, we will use 0. Now, so what we're going to do here is we use the same data as hard binary classification, but we're going to learn a different target function. A different function, previously we learned binary classification, now or next we are going to learn a soft binary classifier. And Before we end today's class, I want to quickly show you the hypothesis we're going to use for this. And I'm hoping that from the hypothesis, you can now see our ways of constructing the linear model. We have vector features, as always. We have linear weights, as always. And after having the vectors and the linear weights, we compute a score. Remember what we did with the score? We have sign of the score, so we can output -1 or +1. We have the score itself, so we can output real values in linear regression. Now, what do we want to output? We want to output something between 0 and 1 for this kind of soft classification problem. What do? We take a function to convert the score to something within 0 and 1. And that particular function is going to be called a logistic function. It's S-shaped like this, and when s goes to infinity, the output value is close to 1. When s goes to -infinity, the output value is close to 0. That's the logistic function that we are going to consider for this learning problem, this soft classification problem, which is usually called logistic regression. Okay, and in the next slide, I'm going to introduce you the shape of logistic regression, but we are running out of time now, which brings me, first, let's check the questions. Bear me for a few moments. Do we have some questions here? Okay. Okay. +1 here, what is +1? +1 means output +1 or generate a +1 label or y equal to +1. Okay, so we're taking the terminology here. Why is it called logistic? Okay, allow me to answer it in the next class when we actually see the shape of the hypothesis, and also is logistic regression used for classification. We will discuss in more detail in the next class. And why minus the half? Okay, and this particular one we encourage you to derive by yourself. If God tells you the probability distribution that generates binary labels, what's your best prediction? Okay, the best prediction is to predict positive when the probability is more than half, and negative when the probability is less than half. Okay, if you only have two outputs. Okay, so it's just for example, if I give you a flip coin and I tell you the probability of getting a head is 0.8. Now I flip a coin once. Let you guess. Okay, what is the outcome of the coin? What's the most possible outcome of the coin? What's the most errorless outcome of the prediction? You would say head. Okay, because you know that the coin is biased and you can just decide the most probable outcome by comparing the probability value with a half. Okay, sorry for being a few minutes late, and also sorry for being notoriously delayed with our course agenda. That actually means we have not finished everything we want to teach for homework 2. That's bad. What should I do with homework 2 then? Okay, short answer I'll discuss with the TAs, but most likely we will announce homework 2 today, but we will extend its deadline so that we can make sure that you will have the proper knowledge to work on homework 2 for a sufficiently long enough time. Okay, so most likely we will extend the deadline of homework 2, but please stay tuned until the formal announcement. Yay! Okay, thank you very much for attending today's class. I hope you have enjoyed homework 1. If not, if you have not finished homework 1, you still have an hour or so from being late. And we will announce homework 2 soon with possible extensions. Let's just say possible extensions. Okay, yay! Thank you very much. Bye-bye.